Now, most people have come across the pH scale. It's a bit unusual, with the scale running from 0 to 14. The reason for this is that when we use the pH scale, we imply that the major component of the mixture, the solvent, is water. It's the properties of water that define the pH scale. So let's start with water. Pure water. The bonds that hold the water molecule together are strong, but not incredibly so. At room temperature, there is enough energy to break up some of the water molecules. And when this happens, the hydrogen leaves as a positively charged ion, which means that there is a negative charge left on the remainder of the molecule, a hydroxide ion. This is called the autoionization of water, and you can see why. The water automatically dissociates into ions. It doesn't need another reagent to do this. However, these products can recombine to form water again. We have a constant back and forth going on, a reversible reaction. We end up with a situation where the forward reaction is supplying ions as quickly as the back reaction is consuming them. We say that the system is at equilibrium. Equilibria occur a lot in chemistry. Don't blame me, it's just the way it is. Now, when the system reaches this equilibrium, the concentrations of the ions are constant. It's not that the reactions have stopped, it's that the forward reaction is producing the ions at exactly the same rate as the back reaction is consuming them and making water molecules again. If we analyse a sample of pure water, we discover that the concentration of hydrogen ions is 1 × 10⁻⁷ moles per litre. Looking at our reaction scheme, it shouldn't come as too much of a surprise that the concentration of the hydroxide ion is the same as the hydrogen ion concentration at 1 × 10⁻⁷ moles per litre. If we multiply the concentration of the two ions together, forming what mathematicians would call a product, we get the ionic product of water. This is 1 × 10⁻14 moles squared per litre squared and is given the symbol Kw. Providing the temperature stays at or around 25 degrees C, Kw is a constant. This means if the concentration of H+ rises, then the concentration of the hydroxide ions must decrease. Equally, if we start again with our ions at the same concentration, if the hydroxide ion concentration goes up, the hydrogen ion concentration must go down to compensate. Okay, we've got an understanding of how the equilibrium that controls the hydrogen ion concentration in water works, but what about pH? Here's the equation for pH. Yes, there really is an equation. pH is not an arbitrary scale. Notice that pH is related to the concentration of hydrogen ions via the logarithmic function. This means that if we express the concentration in the form of 1 × 10 to the power of x, the log of this number is x. So in pure water, the concentration of hydrogen ions is 1 × 10⁻⁷. The log of this number is -7, and two minuses together make a plus. So the centre of our pH scale is 7. Hence, our pH scale covers an enormous range of hydrogen ion concentrations from 1 molar to 1 × 10⁻14 molar. Due to the minus sign in the equation, when the hydrogen ion concentration is high, the pH number is low, and this indicates an acidic solution. When the hydrogen ion concentration is low, the pH reading is high, and we have a basic solution. However, you have to remember that the foundation of the pH scale is that the solvent is water, and that's why it runs from 0 to 14 with the centre of the scale at 7.